Swayam Prabha. Digital India. Educated India.
So, in the last lecture we saw that electrons, neutrons, protons, all these microscopic things have a dual nature, they have a particle nature as well as a wave nature. And as you would know, the most important characteristic of a wave is its wavelength. And for a particle, you would obviously say one of the most important things is the momentum. And in fact, a relationship between the wavelength that is associated with the particle and its momentum was suggested by de Broglie. We will discuss the de Broglie relationship later, hopefully, but let me just remind you, because you would already be familiar at least a little bit with this. Let me remind you what the de Broglie relationship is. According to him, imagine that you have a particle that is moving with a momentum which we denote as p. So, here is my particle, it is moving with a momentum which I shall denote by the symbol p. Then according to him, you say this particle, because of its dual nature, it has a wave nature, and wave, there should be a wavelength associated with the particle, and so if I draw the wave would be something like this. And when I say the wavelength, what is the wavelength? The wavelength is this distance, this is the wavelength of the particle, and de Broglie suggested that the two are related. Wavelength we will denote by the symbol lambda, and he suggested that lambda is given by the relationship, it is equal to h by p. Now, it is very interesting that de Broglie actually belonged to the royal family. He was a prince, and originally he had wanted to study history. He was a student of history, but then he found history not very interesting, and he switched over to physics. And this was his PhD thesis. The suggestion was his PhD thesis, and people did not believe in these suggestions, and the thesis was likely to be rejected. And if it was not for Einstein, it might have been rejected, and Einstein said that maybe there is some truth in the suggestion, and therefore the thesis was eventually accepted. But then at the time of the viva voce of the thesis viva voce examination, the examiners actually asked him, I mean, this is all theoretically, can you suggest some experiment which will verify this relationship that you are suggesting? And then he said, you know that in the case of X-rays have a wavelength which is comparable to the spacing between atoms in a crystal lattice, right, and therefore you can see X-ray diffraction, because the wavelength is comparable to the spacing between the different atoms in a crystal lattice. So, maybe what you can do is you can have electrons, you can make them in such a fashion that their wavelength will match the spacing between atoms in a crystal lattice, and then maybe it will be possible to see the phenomenon of electron diffraction. This was suggested by him, and it was experimentally observed within 2-3 years, and therefore the relationship was experimentally verified. So, what I want to tell you is an important consequence of this. One important consequence of this is actually the Heisenberg's so-called Heisenberg's uncertainty principle. So, to demonstrate to you how the uncertainty principle comes around or comes about, you imagine that you have a particle, this is the particle that is moving with a momentum as I have indicated p, and the momentum, I know precisely what the momentum of the particle is. If I know the momentum precisely, then of course I will know the wavelength. If this relationship is valid, I will also know the wavelength precisely, and the wavelength will be given by this relationship. So, I know precisely what the wavelength is, and so what will happen is that I will have a wave which looks like this, and its wavelength is very well defined. So, it will be repeating again and again with a periodicity that is equal to lambda. It will go on repeating again and again and again and again. In principle, it will extend from minus infinity to plus infinity. On the other hand, if I had a wave which is probably something like this, suppose I had a wave which is of this form, then it is not possible to say precisely what the wavelength is, because you see this distance, would you say is the wavelength, or would you say that distance is the wavelength. So, wavelength is ill defined for such a wave. So, in order to have a very well defined wavelength, I should have a very long wave with it repeating periodically in this shape, sinusoidal in shape, so to say. It has to go on repeating. So, therefore, if you say okay, this is the kind of wave associated with this particle which has a well defined momentum, and then if you ask me where will, suppose I do an experiment where I am going to find where the particle is. Suppose this is the wave associated with the particle, I mean this is eventually going to be associated with my wave function, this wave that I have. So, we know that where maybe what I can say is okay, wherever the value of the wave is large, I will probably find the particle there if I do an experiment. So, therefore, I mean if you look at this, you can say the way it is drawn, at this location it has a value, and at that location also it has the same value. Even here it has the same value. My drawing is not perfect, but you can imagine it is perfectly periodic, and so you see that there are different points where it has exactly the same value, and therefore you would say okay, if I did an experiment, maybe the particle may be found somewhere in this locality, or maybe somewhere there, or maybe somewhere there, or maybe somewhere there, and so on. So, therefore, you realize that if I did an experiment, the particle can be found in principle anywhere between minus infinity and plus infinity, because my wave extends over such a region. And therefore, what has happened is that externally if I try to determine the position of the particle, I would find that my answers each time is going to be very different. Sometimes I may find it here, some other times I may find it there, some other times I may find it elsewhere. So, I will have a huge uncertainty in the externally observed values of position. That means if I denote the position by the symbol x, there is a large uncertainty in the value of x, huge uncertainty. So, therefore, I will say that this is a situation where the uncertainty in the measured position of x is large. In fact, it would be infinity in principle if I had such a wave. Now, look at the situation, I have no momentum precisely. So, therefore, I have no uncertainty in momentum. Momentum is precisely known for this particle. So, if I had delta p uncertainty in momentum equal to 0, then if I measure the position, the answers are going to be so different that I would have a huge uncertainty in the value of position. On the other hand, if suppose you say no, I do not want this, I do not want the position to have such a large uncertainty, then what should I have? I should have maybe a wave which is of this shape. Right? This wave has the characteristic that it is 0. See, it is non-zero only in this location, in this region, and outside the wave is 0. So, if I wanted to have such a wave, why do I want to have such a wave? If I had such a wave, when I measure the position of the particle, sometimes I will find it here, sometimes I will find it there, maybe sometimes here, and so on, but the uncertainty will not be very large. It will not definitely be not infinity. So, here delta x will be finite, correct, but then you ask what is the wavelength of this? That means the answer is ill defined. I mean, because you have to think of a wavelength for this. We will see how it may be done in the next few pictures. So, this is my first wave that I talked about. The wave actually has a definite wavelength, it extends from minus infinity to plus infinity. Now, suppose I want to construct a wave of this shape, how will I go about doing that? That is made clear in the next few pictures. So, you think of this red wave and you also think of this green wave. If you look at it carefully, you would realize that the wavelengths are slightly different. The wavelengths of the two waves are slightly different, they are not the same. And now suppose you added these two waves, what would be the result? If I am adding these two waves, the answer you can see what is going to happen. If you think of a point here, right at that location, the green wave has a displacement which is downwards, the red also has a displacement which is downwards. So, if you added the two up, you will have a large displacement in the downward direction, right. But if you thought of a point somewhere here, what will happen? The green wave has an upward displacement while the red one has a downward displacement, the two will nullify each other. So, if you added these two, what would be the result? That is shown in the blue curve that is shown here. I have drawn all the three waves. You see this blue wave is actually the result of adding the red and the green, and you can see that by adding these two together, I have managed to have something which looks like this, right. Well, if you actually added the two waves up, what will happen is that you will have this being repeated again and again and again, okay, that is what happens. But the point is that by adding two waves of slightly different wavelength, I can actually make the wave function have a large value in some region and smaller values elsewhere, right. But now suppose I am not going to add just two waves, I am going to add a large number of waves having slightly different wavelengths. Then what I can do is I can have a situation, this is actually mathematically possible to demonstrate, but we will not do that. You will have to believe me when I say I can have a wave which probably is of this form. Its value outside is 0, its value in that region also is 0, and the wave is localized only in this region. All the other regions, you see, I can cancel everything and have an answer 0 everywhere else, but only in a small region. But for that to happen, what I should have is I will have to add together several waves of slightly varying wavelengths, right. And this is something that we can refer to as a wave packet. The mathematics of this I hope to discuss maybe after something like 10-20 lectures. So, that will come later, but this is the idea. So, then this is actually such a wave is a superposition of waves of different wavelengths. Now, why did I do it? Because I wanted to have uncertainty in position small. Uncertainty in position is now of the order of this distance. It is of the order of this distance, and this I shall denote as L. Okay. So, this is a situation where delta x is of the order of L, and for such a situation what has happened? The momentum earlier in this case the momentum was well defined, there was no uncertainty in momentum, but to have this I had to superpose waves of varying wavelength, and so momentum has become uncertain, or the wavelength. Instead of saying momentum, I should say the wavelength has become uncertain. If the wavelength has become uncertain, naturally if lambda is uncertain, then momentum is uncertain. Now, if you want to make this wave packet narrower, you can do that, but then you will have to superpose waves of even widely varying wavelengths, and therefore, the moment you try to reduce the uncertainty in position, what happens? Uncertainty in momentum starts increasing. So, there is an inverse relationship between uncertainty in position and uncertainty in momentum. This was mathematically analyzed by Heisenberg, and he came up with this relationship. He said that he could show, I mean this is something that I hope to do later in the course, but here I am just giving you an overview. He could show that delta x into delta p must be greater than or equal to h divided by 4 pi. Okay, this is one of the consequences of this wave particle duality, and I want to talk about another one which is of great interest to us, particularly when we are thinking of atomic orbitals, molecular orbitals and so on. See, suppose I now imagine that I have a very long string, let me say one end of the string is attached to that wall and I am going to take hold of the other end here, and very quickly what I will do is I will stretch it tight and then I will just move my hand up and down, and then what will happen, I would have produced a disturbance which will travel. Okay. So, or you say okay, you stretch it tight and then maybe I will just lift up a part of the string and very quickly and then release it, then what will happen, I would have produced a disturbance in that string, and that disturbance naturally it will travel on the string and it will reach the wall, from the wall it will be reflected because it cannot go further. So, it is going to get reflected, and what you are going to see is an animation, right, which shows this reflection. So, here imagine this is the, I mean this kind of displacement is difficult to produce, but imagine I am able to produce such a displacement initially, and imagine that it goes towards the wall, then it is going to get reflected, and how will it get reflected, you can see that as an animation, but the way the animation is made, you see the reflection process is shown again and again and again several times. Okay, that is how the reflection process actually takes place. It goes, hits the wall and is reflected. So, if you had a wave in a medium, what is it? I mean I have a string, that is my medium, and I have produced a wave. The wave is moving in the medium, but then if I put an obstruction, what will happen? I would have reflections, right? I would have a reflection from the obstruction. So, now suppose I put two walls. So, therefore, I am going to now imagine that I have two walls here, let us say, and I have a string which is stretched tight between the two. So, then imagine that, and then what I will do is I will take my hand and hit the string, and then what will happen, the string will start vibrating. You can see the kind of things that it can do in the next animation. So, here what is happening is that you see the initial displacement that I have produced. It is this one, this is my initial displacement, and it goes on changing its shape and so on. So, what is happening is that the wave is reflected from, not from one side alone, but it is reflected from the other wall also. So, therefore, you have reflection from this side, you have reflection from the other side, and also you should notice that the shape of this disturbance that I have produced is going on changing, it is going on changing all the time, right, that is what you see. But then in the case of a string, we know experimentally that it is possible for one to produce certain special kinds of displacements, right, they are special and they are very nice. Let me show you one of them and tell you how this actually comes about. So, this is a special kind of displacement. You can see that the whole of the string goes up and then goes down, and it is going up and down with a certain number of times in a second. So, that we refer to as the frequency of vibration of the string, it goes up and down with a certain definite frequency. Here what is happening is that the disturbance that you have produced, it is definitely getting reflected from this side and from the other side, but what has happened is that the original disturbance and the reflections actually combine to retain the shape of the disturbance. See, in the earlier disturbance that I have shown, that was not the way it was, there were reflections and the reflections were actually causing the change in the shape of the wave, but that does not happen in this case. Here what is happening is that there are reflections, but the reflections and the original disturbance are such that they manage to retain the shape, and this is referred to as a standing wave pattern. And further, you see, earlier you would have seen that the disturbance is actually moving back and forth. So, you would have referred to it as a travelling on the string, but in this case, see, it is not moving back and forth on the string. All that is happening is that the whole string goes up and down, it goes up and down in the perpendicular direction, not on the string itself. So, this is something that is referred to as a standing wave pattern, and it is special. Why is it special? Because first of all, it has a definite frequency. The second thing is that its shape is not really changing, right. When I say shape, you see it is shaped like this, and the magnitude of the displacement actually changes, but other than that the actual shape is not changing. But this is not the only standing wave pattern that I can imagine. These are also referred to as normal modes of motion of the string, and in fact this is the simplest possible normal mode of motion of the string. But suppose you had sort of other possible normal modes of motion. This is another possible normal mode of motion, where what is happening is that the half of the string, imagine it is going up, then the other half is actually going down. So, it vibrates like this, and further right in the middle of the string, at this point what is happening, there is no displacement of the string, right. The action is happening not at the middle, but elsewhere. So, that particular point, actually at that particular point what is happening is that there is no displacement of the string, and therefore, I will refer to that is a special point, and I will say that it is a node. So, in this case, in the case of a string, you would say, agree when I say that the string is a one dimensional object. What has happened? I have a particular point where there is no displacement, and that is referred to as a node. So, here the node is actually a point. That is the case of the string actually. And string, of course, you will agree when I say that it is one dimensional, it is a one dimensional object, and a point, mathematically speaking, its dimension is what? It is 0 dimensional. Now, this is another normal mode of motion. You can think of other normal modes of motion. This is yet another one, and the major difference between this and the previous one is that this has two nodes. And what about the simplest one that we had? The first one you can see again, this is the first one, and this obviously has no nodes, right. So, the first one has 0 nodes, the second one has 1 node, the third one has 2 nodes, and then obviously you can imagine other normal modes of motion, they will have 3, 4, 5, 6 etc. nodes. And so, in principle, if you do not worry too much about the atomic structure, and if you are asked the question how many normal modes are possible, then the answer is infinite. They are all characterized by the number of nodes 0, 1, 2, 3, 4 etc. So, infinite and one more point, maybe I should simply write simplest mode, it has no nodes. So, this is the next one. and all of them are, I mean the 4 that I have shown you are all shown here, but of course it is easy to think of the other higher modes. Okay, this is just an interesting thing. This again has nothing to do with quantum mechanics. Actually, this shows you standing waves can be set up in a bridge, for example, and something very unfortunate happened long ago, around 1942. This shows you. This is a video which I will play for a few minutes. There was a very famous bridge. It is referred to as the Tacoma Narrows Bridge. This is in the US. It was a very long narrow bridge, and it was built around 1940 in the around 1940-41, and this was in a region where there were strong winds. And after the bridge was built, it was found that because of the winds, there were standing wave kind of things set up in the bridge, and these standing waves, I mean there was some kind of resonance. The waves that were set up were very large, their amplitude was very large, and so now you can see what the result was. So this is view of the bridge on a particular day, and these were the oscillations caused by the wind. So you can see them very clearly, the modes, the mode that was set up. It's quite interesting if you have not seen it. There is a car sitting on top of the bridge. The story is that there was a dog inside. The man who was sitting, he came out and crawled to safety, but the dog perished because of the collapse of the bridge. And later on they constructed, I mean they realized that the engineering was not correct, so they constructed another proper bridge. This is from YouTube. Okay, well, we have thought of something that is one dimensional, but imagine I have a drum, and the membrane of the drum obviously is 2 dimensional, and normally, as you know, drums are actually having nice circular shape. But let us imagine for a few minutes that I have a rectangular drum. I am crazy, I have made a rectangular drum, let us say. And how would the membrane look like? This will be the membrane, and you should realize that along the peripheries the membrane is fixed. Okay, along the periphery the membrane is fixed. So therefore, if I take my hand and hit it, what would happen? I would have produced a displacement of the membrane, and that displacement will move because the membrane is stretched tight. It will move on the membrane, but it will hit the peripheries, and from there what will happen? It will get reflected. And what is going to happen is that as you watch the shape, I mean if you can watch it, of course, the shape of the membrane will go on changing. Okay, I mean you will have to do speed photography to actually see it, but this is how it will go. I mean if I have taken this and then hit the membrane, there I will have some kind of disturbance which goes around something like this. But just as in the previous case, well, here again the video is not the video, but the animation is repeated again and again and again. But just as in the previous case, it is possible for you to produce what are referred to as standing waves. These are waves whose shape go on changing, but it is possible for me to produce waves which are standing In what sense? They are not actually moving around. Here the wave is actually, the disturbance is moving around. So, this is a very special kind of disturbance or displacement that you can produce. What is happening is that the whole of the membrane goes up or it goes down, and that happens with a particular frequency. And I am sure you will agree when I say that here this is the simplest possible pattern, and that does not have any nodes. There is no point inside the membrane where the displacement is 0. So, that immediately tells me that it should be possible to think of other modes, which is the next one that I can think of, a mode like this. And if you look at this, you will agree that there is one node, right. Where is the node? Actually, if you look at it carefully, you will see that it is this line, this particular line. Along that line there is no displacement, and so it is a node. So, this in the case of the membrane, I hope this is visible. Membrane is 2 dimensional. What has happened is that the node is actually, it is not a point anymore, the node is actually a line, it is a line, and the line you will say, what mathematically speaking, what is the dimension of a line? It is 1 dimensional. So, when you have membrane which is 2 dimensional, you have line which is node which is a line which is 1 dimensional. And how many such modes can you imagine? Well, you can have 0 nodes, then you can have 1 node, then you maybe 2, 3, 4, etc. and so up to infinity, at least in principle. So, you can see that you see this one is another disturbance. So, what is the characteristic? It has 2 lines along which the displacement is 0, and these 2 lines are perpendicular to each other, correct. So, I have shown you 3 of the normal modes, all of them together are shown in this animation, but then I have one more picture. It is not an animation, but it shows you the different modes. This is the membrane is not displaced, but then this is a displacement which has no nodes, a normal mode of motion in which there is no displacement. This has 1 node. This also, this is not the same as that displacement, that also you should notice. What is the difference between the two? You will see that the nodes are actually different. This one has a node along that particular line, while this one actually you cannot see the line is perpendicular to the line in the previous case, right. So, this mode is different from that mode, and then you have maybe a situation with 2 nodes. We have already seen the animation, and then maybe you can have a situation like this one. This one is drawn in such a fashion that there are 4 nodes. So, you can have 0, you can have 1, then 2, 3, 4, etc. in principle up to infinity. So, in the case of the membrane also, what happens? You would have infinite number of modes of motion, normal modes of motion, and the simplest possible one has of course 0 node. Not only that, if you have wave in 2 dimensions, what happens? The nodes are actually 1 dimensional, right. And if you have waves in a string which is 1 dimensional, what happens? The nodes are actually 0 dimensional. Okay. So, there are infinite such modes. Now, as I said, the membrane, a drum is circular usually. So, you may ask what happens if we have a circular membrane that is shown here in this picture. You will see that there are nodes, but if you look at this one, this is the simplest possible standing wave pattern that you can have. It has no nodes, the whole of the membrane goes up and down. If you look at this one, what would you say? Well, here if you look at it carefully, you would realize that it has just one node where the displacement of the membrane is 0, and that one node is actually having the shape of a circle. This one, if you look at it and think about it carefully, you would realize that it has two nodes. The two nodes are both circular. Okay, circles, I mean along the circles there is no displacement of the membrane, while this one has one node, and that node is actually roughly along this particular line, this line, right, the line, a line which runs like that, and this one also has a node which is perpendicular to that line, right. There are two nodes, this one has one node, this one has another node, and the two lines are actually perpendicular to one another, while the last one, it has two nodes, right. The mode itself has two nodes, both are lines perpendicular to each other. Okay. And then if you are asked how many such modes can you think of, again the answer is in principle infinite number of such modes are there. Of course, here also the simplest one, it does not have any nodes, and as you go up, what is happening is that the number of nodes go on increasing. Well, you may ask what is the relevance of all this to chemistry, because you see this is a course on quantum chemistry, and so I should make connections with chemistry. So, let me do that. Imagine that I have a particle. Okay. We will see examples later, and this is confined to a box. Okay. So, let us say, well, to make things simple, imagine that everything is two dimensional. So, therefore, this region is a box, two dimensional box, such a thing it does not really exist, but let us we can have close approximations to this, as we will see in a few seconds. Imagine I have a box like this, and an electron is confined to this box. What does it mean? You see, if it hits the boundaries of the box, it is going to get reflected, which is what is shown in the picture. So, you see, so the electron has a wave associated with it. So, if I am confining the electron to this box, what will happen is that the wave associated with it also is confined, it cannot go out. And if it does not go out, what does it mean? The wave is going to get reflected from the boundaries. So, like the figure that is shown in the picture here, you see that the wave is getting reflected. So, if in such a situation, what is possible? You see, you have waves in a two dimensional medium. That is essentially what you have waves in two dimensions, and you have confined. So, naturally there will be reflections from the boundaries, and then you can immediately say, well, this is like the waves in a membrane, and those waves, if you remember, they could have had a time dependent behavior where the shape is changing, but it is also possible for us to have what are referred to as standing wave patterns. And what can you say about these standing wave patterns? Obviously, I can say that I can imagine an infinite number of such standing wave patterns. The simplest one would not have any nodes, the next one would have one node, the next would have 2, 3, 4, etc. Right? This is definitely possible. The wave associated with the electron can have a state. Notice the word, a new word that I have introduced, can have a state where the wave associated with it forms a standing wave pattern. Right? The simplest state would be that one in which the wave associated with it has no nodes. The next one would have one node, it would have two nodes, the next would have 3, 4, 5, etc. So, different standing wave patterns can be formed, and these are the things that you refer to as stationary states in quantum mechanics. So, what is actually a stationary state in quantum mechanics? This is a state in which the wave forms a standing wave pattern, right. That is what it is. A stationary state is nothing but a state where the wave associated with the particle forms a standing wave, like what has happened in the case of the membrane. So, standing wave patterns in 2 dimensions can be formed. Well, as I said, this is somewhat of an idealization, but this can be realized experimentally, and these are experiments taken from Eigler, who works at IBM. Okay. Well, I will not go into the details of this, but I will tell you what the ideas were. See, what Eigler has done is, he built an STM microscope. STM stands for scanning tunneling microscope. And the beauty of this is that, you see, it is possible for you to image even single atoms sitting on a surface. You can image even single atoms sitting on a surface. Not only that, the one that he built could operate at very low temperatures. In fact, it was one of the first to operate at 4 Kelvin or below. And not only that, you can actually pick up a xenon atom which is sitting on the surface. Imagine you have a xenon atom which is sitting on the surface. You could pick it up using the tip of this microscope. There is a sharp tip using which you can pick up an atom and put it elsewhere. So, therefore, it is possible to move the atoms on a surface. And what he did was, he had iron atoms sitting on a copper surface. Iron atoms sitting on a copper surface. Using this, the tip of the scanning tunneling microscope, he could move these iron atoms and arrange them so that they formed a rectangle which is shown in this picture. Right. You look at this picture, this rectangle is formed of iron atoms, and in fact, these peaks that you see are actually representing the electron densities of these iron atoms, which could be imaged using this scanning tunneling microscope. So, he arranged iron atoms in the form of a rectangle on the surface of copper, and then you think of electrons. You see electrons in copper, right. Suppose you have an electron inside this region, that electron actually it is confined within something like a 2-dimensional box, because you see there are these iron atoms which are acting as obstructions. And so, what is going to happen is that the wave associated with these electrons, they will form a standing wave pattern within the box, within this rectangular box. And if they form a standing wave pattern, what will happen to their electron density? They will have a wave like pattern formed inside the box, and that can be imaged using the same microscope, and he did that, and you can see that there is evidence for wave nature of electrons, because you see the electron density within this has undulations. It varies from point to point with the wave nature, and so you can see that. So, this was one of the very clear experimental demonstrations of wave nature of the electrons. Now, here he has a rectangular box, but why should you have a rectangular box? You can have a circular one, and this is what he did. He put a circular barrier made up of iron atoms, and then observed that the electron density within this actually has this wave like behavior, again proving the wave nature of electrons. This is actually experimental data. This image has become so famous that it is available in many books. You might have seen this already. Well, instead of having a circular stadium, this may be referred to as a circular stadium, you can also have an elliptical one, and even there you can see these interference patterns, right, the evidence of wave nature in the electron density that exists inside this. So, that is from the work of Eigler, but then again you may say, okay, that is all very much difficult in the sense that these are very difficult experiments. What is the relevance of all these things to us chemists in our everyday life, and that is answered in the next 2-3 slides. You imagine you have a hydrogen atom. What is a hydrogen atom? You have a proton and you have an electron. And imagine that I have a situation where the electron has been put close to the proton. Then I know that the proton is positively charged, the electron is negatively charged. So, there will be attractive interaction between the Coulombic attraction that will actually lower the energy of the system. So, if I started with the electron close to the proton, the energy of the system I expect will be low, and unless I supply energy I cannot take it far away, I cannot take the electron far away. If I wanted to take the electron far away, I will have to supply energy from outside. If I do not give that energy, then what is going to happen? The proton is going to be in the vicinity, sorry, the electron is going to be in the vicinity of the proton. So, if it goes in this direction, suppose it goes in that direction, then it will not be able to go to infinity, it will have to eventually turn back, right. So, what will happen to the wave associated with the electron? The wave associated with the electron also will turn back. So, effectively, even though I do not have actually a boundary, what is happening is that the proton is there and the attractive interaction with the proton actually puts something like a boundary, not exactly a boundary, because the electron cannot go far away, it is going to get turn around, that means essentially it is going to get reflected. So, what will happen? The wave associated with this electron, it will get reflected, it is confined, it cannot go to infinity. And if you have confined waves, how is the confinement done here? It is simply because of the interaction between the proton and the electron that acts to confine the wave. Once you have confined this wave, what will happen? I can have a time dependent situation where the shape of the wave goes on changing, and that is what happens in spectroscopic experiments. If you are doing spectroscopic experiments, you are actually changing the shape of this wave, right, by external influence. But we are not going to think about that today. What we want to think about is the situation where I have standing waves, right. Suppose the electron, you think of the electron, it can have the wave associated with it forming a standing wave, and what can you say? You can say, okay, the simplest possible standing wave pattern would have no nodes, the next one would have one node, the next one would have two, the next would have 3, 4, etc. How many standing wave patterns can you form? Infinite number, right. And each such standing wave pattern is what you refer to as an atomic orbital. Remember, this time the waves are actually in 3 dimensions. The hydrogen atom is a 3-dimensional object, it is not 2-dimensional. So, the waves are in 3 dimensions. So, if you think of nodes, what would you say the dimension of the node is? See, you look at what happened. If you had a string which is 1-dimensional, node is a point, 0-dimensional. For a membrane which is 2-dimensional, node is a line, right. So, if you had waves in 3 dimensions, naturally the nodes will be 2-dimensional. So, what would you expect as far as the hydrogen atom is concerned? Maybe a node could be a plane, because a plane is a 2-dimensional thing, or it could be a node could be the surface of a sphere, because mathematically speaking the surface of a sphere also is 2-dimensional, okay, because even though it is exists in 3-dimensional space, you see the mathematically it is a 2-dimensional thing. So, therefore, it is possible to have standing wave patterns, and what are these standing wave patterns? They are atomic orbitals. The simplest possible standing wave pattern actually gives you s orbital, because the shape is well known. I have not represented it here, but we will discuss it later during the course. This is a p orbital of the hydrogen atom. It has one node, as you are very likely to know. This is a dz square orbital. It also has, nodes, but it has 2 nodes. Then you can have dxy, again this 3dz square and 3dxy, these are having 2 nodes each. This is fz cube, it has 3 nodes. Then another one which may be referred to as gz to the power of 4, it has 4 nodes. So, what are they? They are nothing but standing wave patterns. So, in quantum mechanics, of course, these are referred to as atomic orbitals, or as stationary states of the system. Okay, I think I will stop.